of transmission lines. Before we did the calculation of inductances in transmission lines. Now we are going for capacitance, and in today's lecture I will explain in the same way as I explained before about the inductances. And today we will discuss about the capacitance of single line, then we will go for single phase two wire, and then we will go for three phase, the same like we did in terms of inductances. And at last we will solve a problem related to capacitive reactance, that how you will calculate if some problem, in case of any numerical problem, how you will calculate the capacitance of transmission lines. So in the same way, firstly we will study that why transmission lines have capacitance. Because you have seen that if, for example, we have transmission lines like very near to each other, maybe sometimes 3 meter far away, 4 meter far away, but still they behaves like parallel plates. And you know that capacitor is a thing that if you put some insulator in two parallel plates, it will become a capacitor. So transmission lines behave like parallel plates and air act as insulator. So whenever you put an insulator between two conductors, it will have capacitance, like in high voltage equipment, or like simple, it is a construction of it's the transmission lines just have same construction as a capacitor. So there is electric field generated inside the when you place an insulator between two conductors, it will stop the flow of current, the flow of charge. So one plate will accumulate the positive charge, another plate will accumulate the negative charge. So between these two plates, current cannot be flown. So insulator will stop the flow of current, so there will be electric field. So there will be electric field between transmission lines. So there is capacitance in transmission lines. It is denoted by C. It also depends upon the length of line, like inductance. It has unit, that farads. So we move towards the firstly the single wire capacitance. Don't look at this formula first. So firstly, you know that this is let us consider the microscopic view of a line that has the radius r, and we want to find the capacitance at this point, the same as we did in terms of inductance. So the difference is that in case of inductance, we consider the distance from the middle of conductor. So here we can consider it like this, from the surface of conductor. You don't need to go far. I'm explaining why. Because we always measure the distance from the surface of conductor, because one conductor only have one type of charge, whether it is phase or neutral. So same charges repel each other. So if a conductor just have a positive charge, it will repel the positive charge and pushes the charge towards the surface of conductor. So we can say that inside this conductor there is no charge, but at the surface it accumulates charge. So I consider it as a phase line. So I consider here the positive charges, that this conductor have positive charges outside of its surface. So I want to find capacitance over here. So what I will do, just like Gauss's law, we know that the electric field at any distance x, at any distance, electric field will be q divided by 2 pi epsilon into x. Actually, it's come from Gauss's law. If you will see Gauss's law, you will find this equation over there. So we're starting towards the electric field, and we know that, okay, so we know that V is equal to E multiplied by D. E is electric field. If we will multiply electric field with distance, we will get voltage. I think we have learned this in physics, that we will multiply V is equal to E multiplied by D. If we will multiply the electric field value, electric field intensity with distance, we will get the voltage over here. So here we are actually taking integration of all the distances reaching starting from R. R is the distance, okay? R is the distance from the center of the conductor. Why we are starting from R? Because I have already explained that the charge will be accumulated by outside of conductor. We can say that there is no charge inside the conductor, because charge pushes the same charges repel each other, and all the charge will be accumulated at the surface of conductor. So we ignore this distance from 0 to R. We just take distance from R to D. So if I will multiply, or you can say that if I will add up this distance and then multiply with electric field, so how I am adding distance from R to D into dx. You know that integration is used for area under the curve or adding values. So I am adding the distance from this point to this point, and that is R to D into dx, and electric field, and multiply with it electric field, and then I will get the voltage at point A. So I will put the value of V is equal to E multiplied by D. I will put the value of Q divided by 2 pi epsilon naught into X. I will put here, okay, X is a distance, okay. It may be 1 centimeter, 2 centimeter, 3 centimeter. I just took it as general, that at some point distance X, okay. So I will take the integration from R to D. So after integrating, after putting the value as of VA, I will put the value Q divided by 2 pi epsilon naught into X here, and you know the integration will be applied on, because I am this is the distance, okay. As we know that this integration is will only be applied on a variable X. So I applied, you know, the integration of X is natural log of X. So I will put here, here is natural log of X. So upper limit minus lower limit, natural log of D minus natural log of R. So I can write D divided by R. Okay, this is a log formula. Log M divided by N is equal to log M minus log N. So upper limit minus lower limit, it is integration. So I will get log D divided by R. So as I know that Q is equal to CV, we have learned this in a high school, that if I will multiply capacitance with voltage, I will get charge. Okay, so from here I want to find the capacitance, because I have to calculate the capacitance of transmission line. So C is equal to Q divided by V. C is equal to, so I will put the value of V, this VA at this point value here, then I will get capacitance. Okay, just put this value in this formula and you will get capacitance. C is equal to 2 pi, because here it will be divided, 2 pi epsilon naught is divided, it will go on this side, it will be multiplied. So I just C is equal to 2 pi epsilon naught divided by natural log of D divided by R. So this will be the capacitance at point A of any line. Okay, if you have any confusion, you can ask now until now in this slide. Okay, actually I cannot, you can. Okay, so we, okay, so by moving forward, okay, this is the actually now I'm telling you one more thing, that this epsilon naught, we can take it as ER. Okay, in terms of like normal, we take the value of relative permittivity 1 is equal to 1. It's basically here you can put epsilon, no problem, but normally we take the value of relative permittivity permittivity is 1, so I just put 1 here and got this one. So don't be confused if in problem it is written that the relative permittivity is not 1, it is 0.5, then you have to multiply this epsilon naught with 0.5. It's just normally in normal problems, in all of problems, we take it as 1 relative permittivity. If it is not given, we always take it 1. So this is the formula of single wire capacitance. Okay, so now I will move towards the one thing here is very important. R is not GMR. Okay, like in inductance, we take R as a GMR, geometric mean radius. But here, this R is not GMR. This is simple the radius of conductor, because in inductance, there are two types of inductances. You just recall from the last previous lectures that we always if we want to find the inductance, we always add internal inductance plus external inductance. But here, as I explained, that charge is accumulated on the surface of body, on the surface of conductor, so we are not considering any charge inside, so there is no capacitance inside. So we will just put there is no effective radius. Okay, this is not inductance. So we are talking about charge, and we will just put the value of R is a normal value. We are not talking about GMR here. There is no GMR in capacitance. We just put the value of R, simple radius, which will be given in the problems. Okay, so 2-wire capacitance. So now I move towards the 2-wire. As both wires are, so let us consider these two wires. These two wires are separated by a distance d. So we apply the same calculation for each conductor as proved in previous slide. Okay, so I have one wire. I just consider, because current is flowing in this side, so I just consider it. There are two different charges on each wire. One is minus q, other is plus q. Okay, so the radius of first wire is rx. The radius of second wire is ry. So what I'm going to do, the distance between the wire is d. So I know that this is the Vx is equal to Q divided by 2 pi epsilon naught natural log d divided by Rx. Okay, this is the voltage of X conductor at any point D, maybe here. Then voltage of Y conductor at any point D here. It's just like this formula, nothing else. Okay, the capacitance of first wire I will write is like the capacitance of wire X. I will write is the voltage of wire X. I will write Vx. Then the voltage of wire Y, I will just put the value of Y, because distance is same in both cases. The radius is different only. So as I proved before, that voltage is Q divided by 2 epsilon naught into natural log of D divided by Rx. So if the voltage between two lines, so here we are calculating the capacitance of two lines. Okay, at that point, in last slide we just considered a point from a point at some distance from a line, but here we are considering that the distance between two lines. So the voltage between two lines will be, you know that the voltage difference between two lines will be Vx minus Vy. Okay, so if I want to calculate the capacitance between two lines, so I have to know the voltage between two lines. We will apply the same formula as we applied in previous slide. Okay, so Vxy will be the Vx minus Vy. I will take Q divided by 2 epsilon naught as common, and inside natural log d divided by Rx minus natural log d divided by Ry. This is not X, okay, this is Y. So so the same case as we did before, I will just as you know that the natural log of d divided by Rx minus natural log of d divided by Ry. Okay, let me connect the charger. Okay, so I was here. So if you will apply the formula, you will get natural log of d divided by natural log of d square divided by rx divided by ry. So I will take square as a whole square, okay? And I will also just recall we did it in terms of inductances, and we take natural log of m power n, and here power is square, so we will take square here, and then this 2 will be cancelled out with this, and we will get this value cxy. So the distance, the capacitance between, if someone asks you to find the capacitance between two lines, you will just put the value of distance. If you know the value of distance, you put value of distance here and 2 radius. If radius is same, it will be simply r, okay? Because r multiplied by r square into under root, it is r square power under root, it is r, okay? So this is the line to line capacitance, okay? So first thing, in problems, if someone asks to find the line to line capacitance of two single phase transmission line wires, two single phase lines, two single phase transmission line, so you have to use this formula. If you have any question up to this in any problem here, you can ask, okay? Do you have any question up to here? So okay, we move forward. So what if someone asks you to that, okay, in a single phase you have to find the capacitance, because there are actually there, you know that earth will also act as conductor, okay? So sometimes it have been written in the presentation, in the numerical, that, okay, let me close this one. Okay, in the numerical, that you have to find the capacitance between line to line. Someone, it will be asked that, there will be question like that, you have to find the capacitance between line to line, between a line, sorry, this is not line to line capacitance, this is, you can say that line to ground or line to neutral. Okay, so this is the case in case of, and then I think you understood up to here. Now I'm explaining you this formula, that how it comes like this, why here is 2. I'm explaining here that why here is 2. So for example, here, you know that the capacitance, the voltage exactly in the middle point here, the voltage will be 0 here. The voltage will be 0 here, because here is negative side, it is positive side. So the voltage exact in the middle will be the 0. So I can consider the voltage where 0, I can consider it at neutral, N. Okay. So if it is N, then there will be 2 capacitance. One will be here and one will be here. Because you know that N will also act, ground will also act as conductor. So there are 2 capacitances here. I can call it as C, X, N. I can call this one C, X, sorry, C, okay, C, Y, N. So this is CXN, this is CYN. So firstly, you have to get this point, that the capacitance exactly at the middle, capacitance exactly at the middle will be, the voltage exactly at the middle will be 0. Okay. So if I want to find the capacitance Y to neutral here and X to neutral, so it is actually the same distance here and the same distance here. So I can say that the capacitance CXN will be equal to the capacitance CYN. Okay, capacitance CXN will be equal to the CYN. So if two capacitors are in series, so I can find the total capacitance. If both of them capacitance is equal, so I will get CXN multiply by CYN divided by CXN plus CYN. This will be the total capacitance, right? You know the formula of capacitance. C1 C2 divided by C1 plus C2 if they are connected in series, because it is opposite to the resistor. You know the do you know the formula of equivalent capacitance? You can reply me. Do you know the formula of equivalent capacitance? Okay. Can you hear me now?
Yes, I can.
Okay. So, this is actually the if I told you that both of these capacitors are equal. So I can write CYN as CXN, no problem, and CYN as CXN. Okay. So CXN multiplied by CXN is CXN square. I write here. Divided by CXN plus CXN to CXN. So this CXN will be cancelled by power, and total capacitance, we know that the capacitance between two lines is CXY. This CXY I'm talking about, I can also write here CXY. This is the total capacitance, will be equal to these two capacitors multiply by divided by. Okay, so this two will only CXN will be 2 into CXY. Okay, so what I got from this proof that CXN is equal to CYN, as I explained before, because distance is same, the voltage at this point will be 0. We will consider it neutral. So the distance is same, the charge is same, but opposite sides. So we will multiply by it. CXN is equal to CYN into CYN, which will be equal to 2 times CXY. XY is total capacitance between lines. So if I want to find the capacitance, okay, line to neutral, so I will just multiply it with 2. Okay, so I will just multiply the total capacitance with 2, because inductance and resistance is not like capacitance. Capacitance cannot be added like resistance and inductance is. Resistance and inductances are same. If 200 is series with 200, we just add them. 2 ohm is series with 2 ohm, we just add them. But here the condition is opposite. So that's why we got the total capacitance is less than the single X to N. Okay, any phase to neutral. Okay, I can clear this one. And one more thing I want to tell you, that here I did one more mistake. Here is X2 and X2N. So did you understand that if there are two capacitors, if you want to find the capacitance of two wires, between two wires, you have to use this formula. I have proved this one. If you want to find the capacitance of two single phase and you want to find the phase to line, you will line to neutral or line to ground, or you have to use this formula. Okay, these two formulas are different. You got my point?
Yes.
Okay. Yes. So we move forward and we go towards the three phase equal spacing. Okay, the same thing we have discussed before. that what if the conductors of same radius will be placed at equal spacing. So as we know that the capacitance of single wire, okay, will be C is equal to 2 pi epsilon naught epsilon r divided by natural log of d divided by r. We have calculated in the first line, okay, in the first slide. So this is the formula of this will be the same with the first one, because why? Normally what I do, because the distance is same d, okay, if I actually for 3 lines I have to consider the mutual GMD. But what happens here, if I want to calculate the mutual GMD, this is mutual GMD, okay, because now it's 3 phase, we are talking about mutual GMD. So for example, this is the formula of any capacitance of any conductor. This one maybe Ca single phase, only one phase, okay, single wire capacitance. In case of 3, it is equal to the first slide. Why it is equal? Here there are 3 distances, but still it is equal. It's just like inductance. The distance from here to here multiply by the distance from here to here, okay, and then there are 2 distances. I will for example, I'm saying that the distance from here to here, in case of if I want to calculate the capacitance of A, then I will just go for distance from here to here and distance from here to here. So what I will do, I will get 2 D's, this and this, and number of D's 1 divided by 2. Okay, I'm writing here, maybe you didn't get that. So what if I want to apply the same formula as we applied on burial conductors? It's the same thing. So D, if I want to find this D, this is actually GMD. If I consider it as GMD, sorry, not GMD, mutual GMD. So it is A to B multiply by D A to C into 1 divided by 2. So D as dA to B is equal to dA to C. So it is D square. So D square again divided by 2. So I will just cancel out and I will again get same equation. So that's why we are saying that the same is the case in inductance. Okay, last time I forgot to tell you that the same is the case in inductances. So that's why we say that no matter if there is a single conductor or maybe it is connected in 3 phase, but the distance is same in case of equal spacing, in case of symmetrical distance, we just put the value of 1D is enough for us, because I have proved that even if we will put the value of GMD, it will get cancelled out with square. It will get cancelled out with this square because distance is same. So this is the case of 3 phase equal spacing, but like this, not like 1 2 3. This is not equal spacing. Okay, if conductor are like 1 2 3, this is not equal spacing. In that case we have to find DAB DAC for first conductor, then DBC DDA for BC and BA, and then for third conductor, okay, for each one. So what if they doesn't have, the conductors doesn't have the same radius? So if they doesn't have the same radius, then I have to put the radius of each conductor, like RA multiplied by RB and multiplied by RC raised to power 1 divided by 3. Okay, it will be like this. So do you have any question? You can ask up to in this slide. Do you have any question?
Just a second, please.
You understood it? Do you have any question here?
No, I'm just writing the equation. Just a second.
Okay. Okay, I will send you this PPT, but don't write here R, okay? You can just write R1, R2, R3, because this is a multiplication of, if in case of it doesn't have same radius. Look, if it has same radius, let me tell you one thing. Even if it has same radius, we are always calculate these two distances in a same way, d or r. For example, this is the same radius, so r multiplied by r multiplied by r power 3. This is r cube, sorry, power 1 divided by 3 multiply by 1 divided by 3. Again I will get this.
So it's D
So
over R.
you don't get confused in the formulas. The formula is same for everyone. If you will, if you understand the concept, the distance, it's maybe simple r, or it's if it's GMD, mutual GMD or self GMD, the formula will be same. But in case if conductor doesn't have same radius, then what you will do? You will multiply all the radiuses here. For example, radius of conductor A, radius of conductor B. Sorry, don't get confused over here, okay? Let me explain. RA, RB, and RC into 1 divided by 3. But normally, in case of three-phase equal spacing, you always in problems you always you will get the equal radius. So you must have to remember the this formula, this one. This is important. This formula for equal spacing. But in this shape, okay. So for example, I have conductor 1 over here, 1 over here, 1 over here. So this is D. This is D. Then this formula will not be applied on this. Sorry, this formula will be applied, but this distance D will be different, because this is dA to B and then dA to C for capacitance of first phase, for capacitance of B phase, for capacitance of B phase, B to A, B to C. So you must have to know that whether the distances of each conductor, the spacing of each conductor from other conductor is same or it is different. You have to know this. So if you have any question, you can ask in chat, because now I cannot hear you. So we are moving towards the bundled conductors. So up to now we have proved the capacitance of single conductor. Okay. You can ask. You can ask now. You can ask the question.
We have the conductors, like you just draw them like they're beside each other, okay, in a straight line. This means that the D is not equal.
Yes. Let me explain you again. You want me to explain it again?
I just want to know if in the case that the conductors are beside each other.
Okay. Let me. Okay, so I am explaining here that let me tell you that, for example, I have one conductor over here, one conductor over here, one conductor over here. This is also three phase. But what is happening here? That this is, for example, let me write here. For example, the distance between these two conductors is D1. Okay, D. Okay, let me write some digit. Okay, I am drawing. Okay, my keyboard. Okay, so if this one is maybe D1, this is D. This is also D. For example, equal spacing. I have to calculate mutual GMD, because the distance from A to B is same, but distance from A to C is changing. Here, the distance from A to B is also same, A to C is also same, but here distance is changing. So in that case, you, for example, this is 3 meters, so distance from A to C is 6 meters. then what you have to do, you have to calculate mutual GMD for A. So mutual GMD for A will be, okay, for example, this is mutual GMD for A. I can write DA. So I will, what I will do, for example, if it is 3 meters, I will just multiply A to B distance, then A to C distance, it may be, it is 6. Okay. 3 multiplied by 6, then power 1 divided by 2, because I am multiplying 2 distances. Then it will be 18 power 1 divided by 2. So I don't know, it is not same like this one. So you have to watch closely while you are solving this problem, that equal spacing means, symmetrical means they all are at the same space. Equal spacing means. So in unequal space, you must know the, if for example, it is a given question like this, these conductors. One, I have seen one of your questions you have provided me. The conductors were like this. So you have to use this formula. You cannot use this. You can only use this one in equal spacing, in symmetrical, okay, symmetric spacing. But in asymmetric means if they are unequal spacing, like this conductor, these conductors. Did you get my point?
Yes, I got it.
Okay. So I have connected microphone again. So if you have any questions, in because I cannot hear you, you can write. So we are moving towards the, we are moving towards the next slide. Capacitance through bundled conductors, because so we already know about bundled conductors. We are not discussing this again, that how, what are bundled conductors. I told you that if in single phase they are on the same side, single phase, or on the same side, or single phase, in one phase, if there are more than one conductors, we call it bundled conductors. It is same like inductance. Okay, don't get confused over here. It's same. We will just calculate the natural log of self GMD or mutual GMD. The formula will be the same, 2 pi epsilon naught into epsilon r. Okay, we just put the value of epsilon r is equal to 1, so it will become 2 pi epsilon naught. So the formula is same here, like this. The formula is same. What we are doing, we are doing like this. D is the mutual GMD, and this is self GMD. Sorry. Here, I think there's something wrong in this formula. Let me look in inductances. Okay, we are more. Sorry. So if we look on the inductances here, mutual divided by self. Okay, I got it wrong over here. Okay, it's mutual divided by self. It's not self divided by mutual, because we are, it's mutual divided by self. Sorry for that. So formula is similar like this one. The formula is similar like this one, like this one, like three phase. But what we are doing, because we are increasing the bundling conductors, so I will consider radius as self GMD, and other distances will be the same, mutual GMD divided by self GMD. And you already know that how we will calculate the mutual GMD and self GMD. If it's given in question that you have to find the capacitance of same transmission line, you have to find the inductance of same transmission line, you must you must know how to find mutual GMD and self GMD. If you can calculate both of these GMDs, you can find the capacitance. It's not a difficult task. So mutual GMD is that geometric mean distance GMD I already have explained before. So now we are going to so we have completed the capacitance formulas over here. So note down that the capacitance will be in Henry per meter, like Farad per meter. So capacitance is in Farad per meter, just like inductance was in Henry per meter. So capacitance is Farad per meter. So up to now, if you have any questions, you can ask me. If not, then we will move towards. Okay, do you have a question, or we move towards problem? Oh, no questions. Okay. So this is actually a random problem, finding reactance. So now today you will get the answer of your question, that how we find the reactance of capacitive reactance. Firstly, you will go for capacitive. Inductive reactance is also same. I will tell you at the last. For firstly, as we are talking about capacitors today, so we will move towards the capacitance reactance. We will talk about the capacitive reactance. We will find it. So there's 400 kilovolt, 50 hertz. In some books, it is 60 hertz because the frequency is different in different countries. So 400 kilovolt, 50 hertz, 350 kilometer overhead transmission lines. Okay, I just wrote the short form here. It is overhead transmission line. Has self horizontal spacing with 3 identical conductors. Have self horizontal spacing. So you know that the horizontal spacing, what is meaning by horizontal spacing? Okay, so horizontal spacing means this is horizontal spacing, self horizontal spacing of 15 meter. It means that they have self distance of sorry, not 15, is 12 meter, 12 meter here and 12 meter here. So if it is not, sometimes it is given in problem, the diagram is given in problem, but if even it is not given in problem, you must know what is horizontal spacing. This is horizontal spacing. One, horizontal distance 12 meter, second conductor, horizontal distance 12 meter, third conductor. You must know about this, that this is horizontal distance. I will explain in next slide. So it have a diameter of 3.28 centimeter. So with the 12 meter between adjacent conductors, so we have to determine the reactance line to neutral, ohm per meter per phase, and capacitive reactance for line, E is not written here, line in ohm per phase. We have to find two capacitive reactance. This is also capacitive. Okay, line to neutral, ohm per meter per phase. In just we also have to look take care about units over here. Ohm per meter per phase, and here is ohm per phase. There is no meter. Okay, ohm per phase means the total reactance of line in one phase. The total reactance of line, you know that we will multiply by 350 kilometer and we are going to get it. So the total reactance, this is the total reactive capacitive reactance of line. Sometimes it is written like this: they find the total capacitive reactance for in ohm per phase. So we have to consider this distance. So here is diameter. So what will be the radius of the conductor? You know, 3.28 is diameter. What will be the radius? You can tell me. Can you tell me that? If diameter is 3.28, what will be the radius?
1.64
divided
by 2.
Yes, divided by 2. It's easy, so don't get confused over here. So I put horizontal spacing here. So the distance between each line is 12 meters. Okay, A to B. The horizontal spacing is like this: A to B is the first phase, second phase, third phase, A, B, C. There is no bundle conductors, as no here. It is not mentioned that it is bundle conductor. So it is simple: A to B, B to C. That's each phase have one conductor. And if we want to, okay, don't look here. Okay, this is actually the upside down. So don't look on these formulas. We are starting from We are getting capacitance, not reactance, right? Actually, we are getting capacitive reactance. Capacitive reactance. The total reactance is all is very easy. XC minus XL minus X. Total reactance is very easy. Okay. So firstly, we will go towards the capacitive reactance, and I will also tell you that how to find inductive reactance. Okay, if you have inductance, it's very easy. So this is capacitive reactance. There are two types of reactances in transmission lines. First one is capacitive reactance. The second one is inductive reactance. So if you know how to find capacitive reactance, you will also know how to find inductive reactance, and then we will add both of this, we will get total reactance of the line. If you will get total reactance of the line, you will get the impedance of the line. So let me explain you some here, that we as you know that we denote the, okay, I'm explaining this because of your question. You know that we will write like impedance is equal to R plus or minus jx, like this is the total reactance of the line. Okay, so it will include the capacitive reactance as well as inductive reactance. So firstly, you will know, we have to know the capacitive reactance, and then I will also tell you that how you find the uh, mm, inductive reactance, and then we can add both of these, and then we will get the total reactance. Actually, we are subtracting the it actually. So we will get the total reactance of transmission line, and if you will get the total reactance of transmission line, you will get, if you have the total resistance of transmission line, you are going to get the total impedance of transmission line. So for reactance, for capacitive reactance, you must know the, firstly you know the capacitor capacitance. After that, you can find the capacitive reactance. For inductive reactance, firstly you must know the inductance of line, and then we will put in formula and we will get the reactance. So in this formula, we are going to find, in this problem we are going to find the capacitive reactance, and then we will go towards the sorry, firstly we are going to find the capacitance, and then we will move towards the reactance. Okay, capacitive reactance. Okay, for example, if we have three conductors as given in question, that the 400 kilovolt line, 50 hertz, 350 kilometer, three identical conductors having diameter of 3.228 centimeter with 12 meter between adjacent conductors. Adjacent means one nearby second. The distance between these two is 12 meter and these two is 12 meter, but the distance from A to C will be 24 meter, as explained just now before. So from starting, don't look over here because it is just starting from radius. Okay, starting from radius, I will get diameter divided by 2. I will get the radius of line 1.64 centimeter. There is nothing like effective radius here, so it is easier than inductance. Capacitance is easier than inductance. So reactance line to neutral. So what actually here, what we have to find, reactance, this is capacitive reactance. Okay, this is not total reactance. We have to find the capacitive reactance line to neutral. So we have to use the formula line to neutral formula, as I have explained in second slide, that what is the formula for line to neutral. So line to neutral, we have 2 pi epsilon naught r epsilon r divided by natural log of d divided by r. Here d, for D you will consider it for mutual GMD because this is three phase. So I will consider it as mutual GMD, because if it is actually it is not on the same distance, because A to C distance is doubled, it's 2 times. if it is having the symmetrical spacing like A, B and C, then we have just to use this formula is enough. But actually the spacing is not the same. The A to B is 12 meter and B to C is also 12 meter. It is given in the question, and A to C is 12 plus 12, 24 meter. So we are going to consider D as mutual GMD, as I explained before. So our mutual GMD, distance from A to B, which will be 12. I will put 12 over here. Distance from B to C is actually 12 again here. Then distance from A to C is 12 plus 12, 24. So I will get the capacitance from A phase to capacitance from phase to neutral. So do you have any question? You can ask if you want to ask any question. Okay. So moving forward, if you can calculate it by yourself using calculator or something, you will get this amount. Okay, I'm not putting the value over here. Okay, so you can just use the calculator to find this. And one more thing, you can also calculate this value 2 pi epsilon naught epsilon r. Maybe you will get some constant in the book it is written, but here I'm not using I'm not how to say explaining this. I will just explain that okay, the values from A to B is 12 meter, it's B to C is 12 meter, C to A is 24 meter. I will put all the values and multiply, take natural log. As there are three distances, I am putting 1 divided by 3. So it is phase farad per meter per phase. Okay, this is for farad per meter per phase. Why it is farad per meter per phase? Because we are considering for single phase CAN. So now formula for reactance is now here what you want to know that how to find the reactance. Okay, so you must have heard about this formula before. X is equal to 1 over omega C or 1 over 2 pi f, because omega is equal to 2 pi f. So I can directly write it as xc is equal to 1 over 2 pi fc. This is a formula of reactance. If you know the capacitance, you will just put the value over here and then you will get the value of reactance xc. This is capacitive reactance. We denote it by xc. For inductive reactance, we denote it by xl. And what you are going to do about inductive reactance, x is equal to omega l. Okay, inductive reactance is omega l 2 pi fl. It is not 1 over 2 pi f. That is 2 pi fl. It's different. There are two formulas. One is for capacitor, one is for inductor. So capacitive reactance is 1 over 2 pi fc. On the other hand, if you want to calculate the inductive reactance, then you have to put xl is equal to 2 pi fl, not 1 over 2 pi fl. It's 2 pi fl. You can write in your notes now. Okay. Okay, I am repeating over here. For inductive reactance, it's 2 pi fl, or we can write as omega l. Sometimes we just write as omega l. Okay. So for capacitive reactance is equal to 1 over omega c, or we can write that 1 divided by 2 pi fc. You know the value of pi is 3.14 and the value of frequency is 50 hertz over here. Maybe in electronics, if you recall from your electronics course, you know this 1 over 2 pi fc. Okay, so moving forward, this is ohm per meter per phase, because capacitance is in farad per meter per phase. So that's why it is ohm per meter per phase. The unit of this reactance is same like resistance. It is ohm. And I will just put the value of this value 8.149 multiplied by 10 to the minus 12, and I am going to get the reactance ohm per meter per phase. Okay, this is in mega ohm. Sometimes you will look, the answer of this one is in, because it's 10 to the minus 12. 8.149. Then you will if you will put the value of 50, f is equal to 50 hertz. Okay, it is given in question, in problem. F is equal to 250 hertz, pi is equal to 3.14, c is 8.149 multiplied by 10 to the minus 12, but it will go upside and it will be 10 to the power 12, and it will be around 0.39 multiplied by 10 to the power maybe minus 9 or something. If you will use it by calculator, you will get the very high value of capacitive reactance. So why the capacitive reactance is very high? Because capacitive reactance, if it is not high, this is actually the line to phase to neutral. Okay, phase to neutral capacitive. So for example, neutral is over here. So if it phase to neutral, this capacitance is very high because we don't want the current directly flow from phase to neutral. We want current flow from phase to phase because we want the sending end voltage, because if you will look out transmission lines, it will be let me draw over here, then you will get. Okay, this is for example a phase. Okay, for example here there is something like a neutral line, maybe with pole or something, neutral line. For example, this is a receiving end, this is sending end. I want to current flow in this direction. I don't want the current flow in this direction. Okay, so that's why this reactance is very high. We don't want current to flow. This is neutral, this is phase. We don't want current to flow from this side. That's why we put air as an insulator, and this becomes capacitance. So that's why the capacitive reactance is very high. If it is not high, then the current will flow from this side and we will get less current over here, and it will disturb the voltages too. So that's why the capacitive reactance is very high. So we are moving towards moving forward. We are now second part of question is what is the second part of question? The first part of question, we have determined the reactance lines to neutral. Just I have determined ohm per meter per phase. Now the second part of question is capacitive reactance for line. Okay, for one line, ohm per phase. As from the unit, you can say that ohm per phase mean that the total reactance of any phase of a phase, total reactance of one phase. So this is the ohm per phase. It is not ohm per meter. So now moving forward, second part of question, we know that capacitance, we have already have calculated this. So if it was asked in question that find the total capacitance of line, okay, the total capacitance of line, so I will just multiply it with the total distance, you know. Okay, it's easy, but it is written that for example, it is asked that find the capacitance of farad per kilometer. So I will just multiply it with multiply this value with 1000, so I will get it in kilometers. This is in meters, and if I will multiply with 1000, I will get it in kilometers. So it is 10 to the power 3 here. So minus 12 plus 3 is minus 9. Okay, so and reactance. So what about reactance? Now here I am going to explain one thing. The total reactance, capacitive reactance, especially the capacitive reactance, is very different from inductive reactance. If you find the total capacitive reactance of transmission line, what about firstly I am explaining you about the inductive reactance. For example, we have value of XL is equal to, for example, I don't know how much, maybe for example 0.5, for example millihenry per kilometer. So if I want to find the distance of 100 kilometer line, so I will just multiply it with 100. I'm talking in the case of inductive reactance, okay, not capacitive reactance. Please keep in mind. So if I want to find the inductive reactance for 100 kilometers, I will just multiply 0.5 millihenry per kilometer of this value with 100, so I will get the total reactance. Maybe it's like 50 millihenry. Okay, yes, 50 millihenry. So this is the total reactance. Sorry, not millihenry, it's milliohm. Okay, don't get confused, it's milliohm per kilometer per phase. So in case of it is not henry, it is ohm, because we are talking about reactance. We are not talking about the inductance over here. So we just multiply it with 100. So what is in the case of capacitive reactance? For example, XC, I have to ask you a question, okay? So listen this carefully. So if I have 0.5 ohm okay, I can write like 0.5 ohm per kilometer per phase. Okay, this is the reactance of one conductor per kilometer per phase, because per phase represents the single phase. It means the reactance of single phase. Per kilometer is the reactance of. So what will be the reactance of 100-kilometer line? Can you explain this? What will be the reactance of 100-kilometer line?
We multiply 100 with the 0.5.
I cannot hear you. Can you say loudly?
I will multiply the 100 with 0.5.
So that's confusion. That's what I want to tell you, that we cannot multiply capacitive reactance like this. So keep in mind, in case of resistance, you can multiply. In case of inductance, you can multiply. But in case of capacitance, you cannot multiply. I'm telling you why now. Okay, so why we cannot multiply it? You know, the reactance I have calculated over here. Here is XC is equal to 390.6 mega ohm per meter per phase. Okay, so what if I want to calculate the inductance, total reactance of total capacitive reactance of line? I cannot multiply it with distance like we do in case of resistance, and in case of inductance we can do it, but in case of capacitance we cannot multiply it by total distance. So what we have to do, why? Firstly, we have to understand that why we cannot multiply. Capacitive reactance is different than inductance. Firstly, you have to take in mind this. Capacitive reactance is different. Okay, why is this different? Recall the modeling of transmission lines. If you have, we always model transmission lines like this. For example, if someone asks me to model the transmission line, firstly I will write the resistance of transmission line, total resistance, then inductance. Then we always model like here capacitive. Okay, in pi model we do like this, and in T model the resistance, capacitance, and inductance. These are the two models. One is pi model and another is T model. You know that we use it for long transmission line, short transmission line. I'm not going in explanation over here. You know, there are three types of models we studied in transmission lines. Because if someone tell you that, someone asked you that, okay, write the model of transmission line. Okay, draw a model of transmission line. You just write the total resistance over here, total inductance over here, and total capacitance over total here and here. But one thing keep in mind, that resistance can be added in the resistance and inductance both are in series. They have same situation. Okay, the current will be here and here will be the same. But in the case of capacitance, we cannot add capacitors in series. You know this before, recall from the circuit analysis, we cannot add capacitors in series. So what we can add in series is Y, admittance, or we can call it the suspectance. Y is equal to 1 divided by C in case of capacitor. So for example, the unit of Y as a 1 divided by XC, okay, it's not C. So if the unit of capacitive reactance is ohm, then the unit of admittance, capacitive admittance, which we also called it, is susceptance. But I am calling it as capacitive admittance for your understanding. So capacitive admittance is just like, you know, G, conductance is equal to 1 over R. Okay, so admittance, total admittance is equal to 1 over Z, impedance. So the same like here, we are getting the capacitive reactance is equal to 1 over 1 divided by YC, capacitive admittance. You can call it capacitive admittance, or the formal name of this is susceptance. So if, for example, I can add up susceptance y1 plus y2 plus y3, I can add them like this, and it's but I cannot add up reactance. Okay, so uh, so as connected in parallel, so inverse relation. So we go for admittance or susceptance. You can say we go for capacitive admittance or susceptance. So what is capacitive admittance and susceptance? We can sometimes we denote it by BC, and sometimes we denote it by YC. Both are okay. It is inverse of capacitance, inverse of capacitive reactance. So the capacitive reactance is 390.6 mega ohm per meter per phase. Firstly, I have to convert it in susceptance, or you can say that capacitive admittance BC, or YC. I can also write as this YC. YC is equal to 1 over XC. I will just put the value of 390.6 mega ohm per meter per phase here, and then I will get the value of YC 2.56 multiplied by 10 to the minus 12. It's ohm inverse. The unit of admittance is ohm inverse. We sometimes call this MHO, mho. Okay, so ohm inverse, we write it like ohm inverse per meter per phase. After getting this, I can convert it in kilometer. Okay, so for kilometer, I will just multiply by it with 1000. So minus 12 will become minus 9 after multiplying it with 1000, and I will further multiply it with 350 kilometers, and I will get the total admittance of line per phase in single phase, only one phase. Okay, not three phases. One phase admittance, capacitive admittance is 0.0896 ohm inverse per phase. Okay, I just multiplied with total distance and I got this. So but what I need the capacitance, the reactance, I need the reactance, capacitive reactance. So I will convert it again, like YC is equal to 1 over XC, then XC will be 1 over YC. So XC will be 1 over YC. So I will put the value over here, and then I will get the final answer, 11.16 ohm per phase. This is the capacitive reactance. So you want to ask any question? You can ask now. You can ask now.
No, I don't have any questions. Thank you.
Understand, if you want me to repeat something, I can repeat for you.
No, it's fine. Thank you.
Did you understand completely? Understood this one?
Yes, I got a little confused at first when